The ellipse. You will see in this video how to find an equation that represents a given ellipse in the xy plane. By the way, if you like this video, don't forget to like and subscribe to this channel and activate the bell. It's very important for the continuity of this channel. In geometry, an ellipse is a conic section formed when a right circular cone is intersected by an oblique plane at an angle with respect to its base. There is a simple method for drawing an ellipse. Place a sheet of paper on a drawing board. Find a piece of string and insert two thumbtacks at the 2 points so that the distance between them is less than the length of the string. Attach the ends of the string to the tacks, as shown in figure below. With the point of a pencil, hold the string taut. Then, carefully move the pencil, keeping the string taut at all times. The pencil will trace out an ellipse. The sum of the distance from the point of the pencil to the thumbtacks will always equal the length of the string, which is constant. The points where the thumbtacks are located are called the foci of the ellipse. Foci is the plural of focus. We can now state the definition of an ellipse. An ellipse is the set of all points in the plane, the sum of whose distance from two fixed points is a constant. These two fixed points are the foci, plural of focus, of the ellipse. We now can see some features of an ellipse. Every ellipse has two axes of symmetry. The points at which the ellipse intersects its axis of symmetry determine two segments, with endpoints on the ellipse called the major axis and the minor axis. The 2 points of intersection of the ellipse and the major axis are the vertices. The 2 points of intersection of the ellipse and the minor axis are the co-vertices, and the axes intersect at the center of the ellipse. The foci of an ellipse always lie on the major axis. As we can see, an ellipse has 2 radii of unequal size, the major radius and the minor radius. The major radius is denoted by the letter A, whereas the minor radius is denoted by the letter B. From the definition of an ellipse, we know that the sum of the distance from any point on the ellipse to the foci is a constant distance. We now will find the constant distance. Let P be a point on the ellipse. We place the point P on the vertex 1. Let C be the distance from the center to a focus. Let D1 be the distance from the focus 1 to point P. D1 is minus C minus A. Let D2 be the distance from the focus 2 to point P. D2 is C minus A. As we can see, D1 plus D2 is 2 times A. This equation is very important to get the equation of an ellipse. We are ready to find the equation of an ellipse in a Cartesian plane. If the major axis of an ellipse is parallel to the x-axis in a Cartesian plane, we say that the ellipse is horizontal. The center of the ellipse will be H and K, and the distance from each focus to the center is C. We start with the formulas for distance 1 and distance 2. We know the distance 1 plus distance 2 equals 2 times A. We want to get rid of the radicals, so we will move one term to the other side and then square both sides of the equation. Let's expand the brackets and simplify. We square both sides to get rid of the radical again. Expand the brackets and simplify again. We now will use the Pythagoras theorem to relate A, B, and C. Pay attention. We now go back to the equation of a horizontal ellipse. Finally, we obtain the general form for the equation of an ellipse. If the major axis of an ellipse is parallel of the y-axis in a Cartesian plane, we say that the ellipse is vertical. Let's see how it works. The center is at x equals 2 and y equals 3. It means that h equals 2 and k equals 3. We start plotting the center, then we plot the focus and vertex. The distance from the center to a focus is 1, so C equals 1. The distance from the center to a vertex is 3, so A equals 3. To find the value of B, we use the Pythagoras theorem. The value of B is 2 square root of 2. We can see that the points all lie on the line y equals 3, so the major axis is parallel to the x-axis, and we have a horizontal ellipse. Replacing h with 2, k with 3, I square with a, and b square with 8, we obtain the equation of the ellipse. To find the other vertex, we use the value of A equals 3, units left and right from the center. The foci are 1 unit left and right from the center. Finally, we use the value of B to find the 2 points above and below the center. Find an equation for the ellipse with one focus at 0 and 4 and one vertex at 0 and 6. Graph the equation. We start by plotting the focus and the vertex. If the coordinates of this vertex are 0 and 6, The coordinates of the other vertex are 0 and minus 6, as well as the coordinates of the other focus are 0 and minus 4. Because the vertices are at 0 and 6 and 0 and minus 6, the center of this ellipse is at their midpoint, the origin. It means that h equals 0 and k equals 0. The distance from the center to a focus is 4, so c equals 4. The distance from the center to a vertex is 6, so a equals 6. To find the value of b, we use the Pythagoras theorem. The value of b is 4.47. We can see that the points all lie on the line x equals 0. So we find that the major axis is the y-axis. And we have a vertical ellipse, replacing h equals 0, k equals 0, a square with 36 and b squared with 20. We obtain the equation of the ellipse. Finally, we use the value of b to find the 2 points on the right and left from the center. For each of the following ellipses, determine the coordinates of the center and give a sketch of the curve. To solve item A, first we put the equation in standard form. To obtain the equation in standard form, with 1 on the right side, divide both sides by 144. The larger denominator is 16, and we should remember that the vertices lie on the major axis. Since the larger denominator 16 is in the y-squared term, so this is the equation of an ellipse with center at the origin and major axis along the y-axis. This is a vertical ellipse. By comparing this equation with the equation in standard form, we can see that h equals 0 and k equals 0, which means that the center is at the origin. A equals 4 and b equals 3. Applying the Pythagoras theorem, we get c equals 2.65. Finally, we use the value of b to find the 2 points on the right and left from the center. To solve item B, first we put the equation in standard form. To obtain the equation in standard form, group like variables. Place the constant on the right side. The second step is to make sure the coefficient of the x squared and y squared is a 1. For the x squared, we already have a coefficient of 1, and so we do not need to do anything with that. The y squared, however, has a coefficient of 4, and so we need to take care of that. What we will do is factor a 4 out of every term involving a y. Doing that gives. Now let's get started on completing the square. First, we need 1/2 the coefficient of the x and y terms. Then, square each and subtract those numbers in the appropriate places as follows. Next, we need to factor the y and y terms and add up all the constants. To get this into the standard form, we need a 1 on the right side of the equation. To get this, all we need to do is divide everything by 16. And we will do a little simplification work on the y term. To graph this ellipse, we will do as we did before, but since the larger denominator, 16, is in the x squared term, so the major axis is parallel to the x-axis. This is a horizontal ellipse. The eccentricity of an ellipse. The eccentricity of an ellipse refers to how flat or round the shape of the ellipse is. The more flattened the ellipse is, the greater the value of its eccentricity. The more circular, the smaller the value or closer to zero is the eccentricity. We can think of eccentricity as a measure of the deviation of an ellipse from being circular, and we measure the eccentricity by the ratio of A and C. Thus, if eccentricity is close to 1, then C is almost equal to A, and the ellipse is elongated in shape. But if eccentricity is close to 0, then the ellipse is close to a circle in shape.